AI. Of course, again, 21st lecture, today we'll talk about deep learning. Start talking about deep learning. Again, last week we saw machine learning in general, right? So deep learning is a subset of machine learning with a key idea that we're using something roughly approximating human neural networks, but with many layers. But it's a very rough approximation, despite what you might think. We still have very little idea how human brains work. We are using in neural networks, using something we thought of human brains look like 1950s, right? The shocking thing is that this deep learning works so well, even though it's not quite how we function, right? That's the shocking thing, actually, right? So, again, we form our hypothesis, and then we build our models using multiple layers of something that looks like neural networks again, but it's not quite what humans are like, right? So, again, there's a resemblance to the real neural cells is superficial, but it works. That's the thing. That's the kind of funny thing. It's not stupid if it works. Oh, what's happening here? It goes down. I'm getting a unicorn. That's great. Okay. Let's do the cases. And the boundary. Let me see. Hopefully we'll get some build a very tiny neural network. Maybe not today, but we'll get some basics. Just slow today. So basically we have some inputs, features coming in, right? And we will train it to sort of present, give us some output, basically. That's of course the basic idea, right? We have some middle layers, right? We will see that hopefully I have something to show you in deep learning, right? We'll see the pictures here. Yeah, so right. So this is basically, of course, where pretty much all the major progress has happened in AI in the last, let's say, 10, 15 years, of course, especially in the last 5 years, of course. And again, the use progressing, because until deep learning sort of came back in force, there was the idea that you could do something with some other approaches, right? Some other machine learning approaches would win, right? Some things. Because one of the things with deep learning is that you don't really have, it's almost impossible to get a real understanding what's happening, right? What's happening in a network, right? You can sort of, it's just like trying to expect your own human brain, right? I mean, we have made the best progress of some platform, which is like 400 neurons, right? That's the best we have done so far. And we don't have 400 neurons, right? We have like 80 billion, or what was it? Or trillion? I forget now. Billion? Trillion? What do we have? A lot, right? At least a lot more than this platform, which is like 400, right? And we still kind of you're not completely sure how this neural network in this little tiny worm works, actually, this little platform, right? Which is really basic, right? So it looks like we have a long way to go, right? So basic idea is that we have layers, so something like this, right? You see in the picture, all right? Let me show you this picture, right? So a shallow model, meaning, so this is basically a linear regression model. It's bigger, right? Yeah, so it's still bigger for now, right? So very shallow model, right? As something comes in, right? We have the features, right? We have some simple calculation, right? Have a short computation, do some math, a little bit of math, and out comes the result. That's our basic linear regression model, right? So this would be a decision tree model, right? With inputs, right? And we keep asking questions. Remember how decision tree works? Yes, no, is it bigger? Is it more expensive than that? It has so many rooms. We check on each different feature, we ask questions, and eventually we come up with some answer, right? That's our model, right? However, with a deep learning model, right? To get the final answer, whether it's a dog or a cat or a bird, right? we go through many stages. So the calculations basically are non-linear, right? They're it's not going to be linear, right? There's not going to be a simple formula, right? If you have a simple formula, you have this basically, right? So, and again, and the thing is, this is still in a black art stage. You have some core principles, you have some ideas, but basically a lot of improvement in the last few years has been basically by people like you, like me, many other people, right? You have access to good resource, playing around basically, right? Playing around with features, playing around with depth, right? Trying to see what makes sense, right? Experimenting with these networks and sometimes getting surprisingly good results. Again, one of the things which you'll see is that amount of data we can feed in is more important sometimes than the complexity of the network. It doesn't have to be very deep, right? 4 or 5 layers, right? 1, 2, 3, 4, 5, right? And then we have the output, right? That might be completely normal, for deep network, right? When you have 100 layers, probably not gonna be needed, probably. Some good use of that, right? So let's see some ideas here, right? So simple feedback networks, right? So feedback feed forward, meaning information only goes one way, right? You have some features, some data, some encoded data, generally floats, come in, and they keep going forward, and eventually we end up with some result, right? And hopefully the result is important, right? So, and you may say, what's the difference? Recurrent networks, where some of these calculations go backwards to the layers, right? So sometimes if you have a recurrent network, something goes back, right? In this case, actually something could go back, right? From this you can see that this is probably not a fast forward network because some things you're allowed to go back, meaning your calculations that you did forward calculations could also go backwards, actually, right? So for now, we'll look at the simple forward network, right? So Boolean in circuits, right? And we'll get binary outputs, right? So, a very simple network, right? Input layer. So, terminology. Input layer. This is generally this will be your features, right? What kind of data you feed in, right? You have raw data, right? And each feature, right? Each piece of information, whether it's color, price, height, whatever it is, or just some numerical values, it could be just fully numerical, right? Are fed in, and then you have this hidden layer, or this is a simple neural network, right? Just one layer, not very deep, right? And you have an output layer, right? Which actually gives you an answer. The answer most likely is going to be numerical, right? Well, it's going to be numerical. How you interpret is going to be depends how you want to say it's a classification, right? Or it's actually a numerical interpretation, like, so what is going to be, right? So basically, it's extremely complex function which you can't really model as a normal mathematical function. It's basically writing a very complex function. You could say many ifs and else's, right? Many special cases, right? But to write it sort of arithmetically using this network, right? So, right. So, so let's see if we see an example. So basically, right. On let's go talk about some activization functions, right? Basically, another important concept, right? We'll talk about this. We'll see this talk a lot, all right? Show you this picture. Right. So you will see this in you start doing machine learning. You'll see this terminology again. So meaning accusation. When does the result become important? Basically, in this network, in some stage, right? We can apply different type of functions. When you move from stage to stage, with the stage 0, right? Or whether you actually start to present something meaningful. So again, the idea goes back to how neurons work, at least some basic idea of how neurons work, because when neurons interact, there is an activization, basically some information being passed. So these functions, right, they're different ones, right? They add this nonlinearity, well, to when should this information propagates forward or backward, usually forward, of course, right? So this is a logistic sigmoid function. There's a, I believe it's you. I think it's in the book. It shows it's like one plus Euler minus x. I believe this one here, right? I believe this one here, right? You can look at the decimals, check it out actually, if that's the case, right? So plus, right? And this one is tangent h function again. Seem like completely related things, right? Again, they're chosen because of this non-linearity, right? Basically, how at some point, like things stop happening, basically, right? Information starts flowing, right? Basically, right? Until then, nothing happens, right? So you can come up with your own optimization function, right? Of course, you want it to be relatively easy to calculate, right? Because you're doing a lot of these, right? You move information forward, right? You want to determine at some moment whether you want to pass some information is meaningful or not, basically, right? So, yeah, let's get this logistic sigmoid function. Let me show you. I believe it's correct. Yeah, sigmoid function, right? Again, yeah. Yeah, 1 plus e minus x, sorry, yeah, like this, right? Yeah, it's used in artificial ANN, of course. So it's mostly logistic functions, right? Yeah, and that's the formula for it, basically, right? So H-shaped, basically, right? Nothing happens, and something happens, of course, then it goes up, right? So, and then you can play around with it. So tan H also is very similar. Tan H is actually like this, actually, right? So that's why in this example, this is very similar. It's just much sharper, right? Meaning nothing, and then something quickly happens, right? And then, of course, again, it's all steady after that, right? So, actually, I think we can also implement a relu function here. I'll do this one, right? Usually this NP maximum 0x, right? So plus the function, we could also do, yeah. So soft plus on the relu, let's do add that. Since we have some time, let's add also, let's define, sigmoid. No, or logistic, the sigmoid equals, okay, we can do that. Let's plot that one also, right? So we can plot all three, right? So we're using some vector, NumPy is a numerical library in Python, of course, we widely used in machine learning, pretty much. It's really CRAs underneath, but it's basically pretty much all the fancy machine learning libraries used underneath. So all the ChatGPT, all everything is basically not underneath. Of course, not directly, but as part of some larger overlaying library, actually. So now, let me do F3, right? 3 equals sigmoid, of course, right? Now let's plot that as well, right? Let's plot by 3. And we need a sigmoid, legend, also not sigmoid, okay, comma, yeah. And time, a legend, and time, okay. No? And grid, show grid, and we have some colors, right? It's a color to 0, okay. Horizontal, vertical line, okay. Right, so get some text. Okay, let's see what happens. Do we have colors? Okay, let's take a look. All right. Sigmoid didn't work as well as I wanted because, of course, we have 1 here, right? So we actually want to limit it to -5. No, let's see, -5. Let's double check. 1, right? So this one, okay, yeah. You can see different scales, right? Different scales. Soft plus, right? This is Tanesco Relu, right? Is of course no, so this is correct. This is correct, right? In this case, it's 1. This scale, of course, you stop here. You might, of course, limit here also 1 if you want, right? So different optimization functions. Okay, so let's do a simple gradient descent, right? So we will update the weights. So we'll have some data, right? And we'll have random data completely. We'll have random data, right? And basically, we will be basically moving to the next step, basically by using simple derivative, basically of where should we go, right? Remember that how with descent approach, gradient descent, we look for the slope, right? We go for the, either up or down. In case it's up, right? We look for the, next, where to go next, basically, right? So we'd like to, of course, get some idea here, right? We'll get some results. We see some results. All plus, right? Let's see some results. Maybe very simple example on the results. Print results and all the data. Put the line. I don't know. We're going to plot it. We'll see. I don't know if it's going to show anything interesting. Actually, it will look like well, since we give complete garbage, right? Weights. What sort of data look like? Random seed. Y is 2x plus 1 plus np random 100. Okay, so there's a formula, 2 times x, right, plus 1 plus some randomness, right? So there's some linearity, but I see a lot of randomness, random number from standard normalization, normalized distribution, right? So, 100 random. So there is some noise, plus also there's some randomness. So we will see this, right? So let me show you what this gives actually, right? Let's expand, let me show this. Maybe here, scale B. I'll give like maybe 20 samples, right? 10 samples, right? 10 samples, let's do 10 samples. Not bad. Let me see this. Yeah, okay, right. So notice sometimes it's a normal distribution, right? Right, so we can plot, let's plot this. Let's plot this normal distribution of 10 points. Normal distribution, right? No, I don't know this. No. This is of course just normal, right? There's some points, right? So we will see this sort of plotted distribution found there. Come on, right? No, sorry. Just plot scatter. Yeah. Let's take a look. It should look like as a bell curve. Unless I'm completely wrong, this should look like 3,000 points. We'll see. This looks better. But then we go wrong. It's not the same side. Okay. No, distribution is 100. Range. I believe this is a range. It's 100. Let me stop. So size. Let me print this. Print. Length. What am I doing here today? Doing length. Come on. Let me see. I can't. That's wrong. Let's see. Blend of distribution. That float. Or did I do it wrong? Round X. Let me see. No, this is here. What did I do? No, okay, that's a different function. Okay, let's see. Random. No, sorry, it's random n. Okay, sample. Okay, this is the one. Just to show you this is what should have given you. Yeah, okay. Oh yeah, but this looks like a mess, right? It's not that they want it. I know, but let me see here. Because of course we don't know the order, right? It goes up and down. So what do we want to do? To see anything? Because of course it's not these numbers don't mean anything, right? So how do we? We want to sort. Let's sort it. Yeah, let's sort it now. Let's sort. Yeah, let's do it. Sort. Let's sort it. Yeah. No, let's do this. That doesn't make sense either. So I hope it's not. That doesn't make sense. But normal should have been stored in space, in place, right? Interesting. Did I not in the array? In place, stable, in place? No. Okay, let's see. What did I do wrong here? X, Y, right? These are the values. Oh, no, I didn't. Let me see. Well, I guess we want to show the frequency actually, not the right. This X value, Y would be often it happens, actually, right? So we want to show actually histogram. Yeah, let's don't need to sort. Actually, don't need to sort it. Right. Let's show. Let's show histogram. Yeah, I think so. That should do it, right? All this is not right. Yeah, that's more like it. That's what I want to say, right? Makes sense. Again, so what's the idea? That if you remember your statistics, this is about 68% roughly, right? 34%, right?
Yes.
Yeah.
Standard deviation.
Yes, standard deviation, right? And then this means that it is possible. So in this standard normal distribution, it's possible that really long tail somewhere here, right? Just extremely unlikely, right? So it gets like the first 2 or 3 standard deviations, you will have 99 something percent of the the bell curve, right? Right. Yeah, this is 34, 13, right, on 0.2.1. So yeah, like by 4 standard deviations, you're pretty much almost 100%. But still, it's possible to get something really, it's possible to get 1 million, right? But extremely, extremely likely, right? So, okay, so now we see what it is. Okay, so idea was this, basically we have some randomness, right? So idea is this is y, right? We have basically a formula 2 times x plus 1 plus noise, basically, right? So, and we are going to try to predict this, basically, right? What's happening underneath, right? We have some linearity, we also have some randomness, right? We have some weights, stuff is nothing, right? And then we learn. Let's see if we can learn anything. Let's see if we'll see anything here. I don't know. Take a look. What's our optimization function? So, is this going to work? Yeah, all right. Actually works pretty decent, actually. All right, actually, so we see this. These are these dots, these blue dots, represent of data, basically, right? And again, we don't know what's under the idea. Of course, here we are cheating, right? We know what actually is under. We know the real truth, right? We know the truth is 2 times x plus 1 plus some randomness, right? But of course, in real life, you don't know that. You don't know anything. Right? We're trying to, again, all models are wrong. We're trying to build a model which tries to predict some values. So in this case, for simple, for one-dimensional update, right? We try to basically for update weights and try to come up with a model which can, basically model this, right? So eventually we get something like this, right? And after length, right? I think we printed all different values, so eventually we get to this part here. And again, this is really simple example, basically, right? So, right, so, again, there are a lot of similarities in our networks to Newton's method of finding the root of a function, right? So, basic idea, we approximate the function, on we have a tangent line. The current case, we keep improving, right? So let me see if I can show an example of the algorithm. Let's show a simple example of finding a root using so anything you see in Newton method, right? You probably see this again. So this is not the Alright, so basic idea is this, right? We have a guess, we keep improving, towards right, towards the gradient where it should be, basically. And the cool thing is, what's the word? It goes, just lost the word, not iterates, but approximates very quickly. It moves, it converges very quickly, right? So it's actually used also in your calculators, finding roots of something, actually. Very full algorithm, actually, right? So, yeah, so quickly, right, we keep finding one guess, we keep it again and again and again, right, and we eventually converge, right? So, really cool thing. So, right, so idea is basically, so this is how we adjust the weight. So that's basically, the previous weight can be adjusted, to hopefully to improvement. And what we have, of course, is, right, so basically, so we need constantly, we need to calculate derivatives, basically, in our neural networks. That's one of the takeaways. So when you train something really large, it's happening basically constantly for multiple sections, basically, right? Again, it's not like a regular, derivative 2 to the x, x squared, right? If you know the formula, right? It's so it's of course very simplistic, right? So what else do you need is, of course, you need some way of a loss function which says how well you are doing, right? You need a loss function, right? Which says, okay, are you getting better? Is this actually working, right? Or is this actually not working, right? So that's one of the other core things. So if you start doing it in machine learning, deep learning as part of machine learning, all the tools will include this automatically for differentiation, right? You don't have to do this, of course, automatically. It will do it automatically for you, right? Your activation functions, loss functions, you don't have to do this manually. So basically, to do deep learning these days, just basically choose, okay, what activation function, what kind of layers they want, basically, right? You play around with layers. Of course, you feed in the data, and of course, what's going to be your loss function, basically, right? And then see if anything good happens, right? Of course, one thing is, this is now, these basic ideas have been also 50s, 60s, 70s, even 80s, actually, by 80s, everything is pretty much sort of set in place, but the results you were getting were not really that good, right? So people thought, okay, yeah, this is convincing, you're using this, these are not real neurons, right? It's kind of, yeah, you can do some stuff, but the problem was that the neural networks really didn't have enough data, basically. The computing hardware was not there yet in 1980s, so 40 years ago. So it all changed in about 2012 when AlexNet used for a picture, for image recognition, used the neural networks. And it beat all the other machine approaches by a mile, basically. It's a big change. And then they realized, okay, that's also by the time the NVIDIA hardware is getting kind of, they use NVIDIA hardware, of course, right? They started getting all these nice drivers, so you can actually use it, basically, right? This is around 2011, 2012, right? People getting good results, and so it was basically like all these people who are doing, some statistics or hardcore mathematicians, they were kind of upset because you couldn't completely explain why were these results, but they're saying, just shut up and compute and calculate, basically, because you're getting good results, right? Empirically, it works. Why it works, right? That might might not ever, right? Exactly. We sort of have a good idea why it works, right? It learns this, but why at some moment, when you have enough data, start working really well, right? So there is this moment where, yeah, if you're given like a 100 piece of data, your neural network is not going to be very good. 100,000 pieces of data, right? Most likely, assuming it has proper labels, something, it will work very well, right? And 100 million pieces of data, it's going to be awesome, right? So, assuming you have enough computing power, right? So you need, of course, a lot of work is basically how you call the inputs. You need to have, of course, Boolean attribute 0, 1, right? So that's plus 1, minus 1, right? Numeric attributes, well, you can use these, but possibly, most likely, you want to normalize them, in the range from -1 to 1, or 0 to 1, right? So, or RGB image. You have a color picture. What do you do then? That includes, that's the problem, right? Obviously, you have also, pixels. That's, you just only 3 bytes for color pictures, 3 bytes, right? So usually there's some array structure. So basically, tensors, right? With multi-dimensional, arrays, basically. But the question is that if you are not careful, this moment you will lose information which is preserved. These 3 bytes are together, basically, right? So all you use for another byte, you have a single byte, but you want to somehow preserve the connection between these bytes, right? So that's an issue here, right? So what do you use categories? I mentioned this last week on machine learning. We usually use one-hot encoding, right? You have like 50 features, you use 50 bits of information, right? So only one of them is true, right? Because that seems to work the best. Because otherwise, because you don't really have again, if these classes, these categories are not related, apple, banana, right? There's nothing says apple is bigger than banana, basically, right? Or vice versa, right? So you need to encode them using one-hot encoding, right? So, so because you don't want to use ordinal relationships, imply. I mean, you might, if you don't think about it, you will get a result. You might, your neural network will learn some unexpected things. Like my thing always prefer banana over apple for some reason, right? That's because you put it into the data incorrectly, basically. So some examples that you can do. Scaling, right? So you have some random numbers, right? So idea is this, right? So scale everything from 0 to 1, right? So there are a couple of things you can do here. Of course, how do we scale, right? You have some data, but the easiest way to do is find the maximum value, divide by that, right? You get 1, maximum 1 then, right? You have data from from 0 to 5 million. Okay, maximum is 5 million, you'll divide everything by 5 million. That is possible. Yes, you might try that. But if your data is not normal distributed, right? There's some features, right? We can do log scaling instead, right? So because we want to, again, to represent this range of data, maybe there's hundreds, thousands, 10,000s. We want to show this in your data, right? Again, it really is the part of preparation to decide whether it's all nicely linear, right? Or maybe there is some exponentiality there, right? So then, of course, if you suspect your feature is exponential, then of course you would use log scaling for this. And so here would be an example, right? We find that X scale, right? This is the other one, right? And we could also do min-max scalar. So there's a couple different things we can do. I would like to, right, you can see how different results we see. Let's say 10 values, right? Let's print them, actually. Print, let me do this, can I do this like this? Only this is going to work. Separator, yeah, I'll do that. We do that, it should work. Yeah. This one print more than one line. Let's see if this works. Control V, yeah, no. Let's see if this works. 3 different examples of scaling. Alright, yeah. So you can see how different scaling works. This was absolute max. That's very similar, actually, almost slightly different, I think, at some point, right? Yeah, I should say, but this is actually would be the first one is max scalar, right? This would be the is mean max scalar that's by shifting, right? So yeah, so in this case, we may want to actually shift it by the minimum, right? We want to shift everything. That will be another thing. So log scale, okay, so this will be log scale, right? So we have a 5 million, no, oh no. We have random that is 5 million, right? So this of course will be a big number, right? And the scale usually can be long, right? So of course this means that this will be mostly, well, we'll see some values, right? Very big values, right? We do any log scaling, right? We will have, of course, already kind of range that is really big, like 22, right? Or 18, that's pretty small, actually, right? Because each number here represents, 1 power of 10, of course, right? So, of course, you can use that afterwards, right, to scale more, actually, right? Again, all of this automatically will be included by your most libraries. Machine learning libraries will have tools, methods, right, in your favorite language, do all this for you, right? Just something you have to consider to do, right? You have to do it. So same thing for one hot again, right? Unique values, right? The rest will be zeros, right? So where the cat and okay, oh yeah. So where cat dinosaur dog fish, right? Yeah, so it's last week actually, right? Let's encode them, right? So I have my features, right? And these are my, again, yeah, cat, dog, bird, fish, dinosaur, right? And I can encode it. And I have my encoder, right? These would be, I have to pass it all 5, of course, right? So we cover that. So, let's see how much time we have. We can do it pretty good, actually, right? So, all the layers. Yeah. Right. So, of course, we are going to be doing result. Again, we'll have to we'll need some to get the format, the data, something is useful, actually, because we want to compare it, what we, what good is it? We get the value, right? You get some value, right, for the network. But we want to exactly, in an ideal world, it will match or prediction or exact truths, right? It will match the true order exactly. Minimizing the loss to 0, right? But of course, in practice, right, the inaccuracies there will be some inaccuracies to quantify the difference, right? So basically, what's happening underneath, basically you'll have is, we'll have a very complex function, right, to given some inputs to produce your number, basically, right? This means we have a model, we'll have a working model, right? So, again, in ideal, assuming you have a training data, right, you check, of course, it should be exactly, right, the value what you're trying to match, of course, right? And then you can use it to some test data and see how well it works, right? So, there might be different ways of transforming this. Now, so inputs, outputs, we prepare inputs, we hopefully prepare outputs, how that we want to see, and then, of course, the hidden layers, right? And again, so up to 2010, they use the sigmoid functions, the ReLU, and so-called functions gain popularity, right? So idea is that this why this work, well, okay, it's not completely proven, but of course, the idea is it breaks this complex model into smaller steps of transformation, right? So this learning aspect of these multiple layers, each layer sort of adds its own understanding of some specific feature. So that's a theory behind basically, right? So again, if you have, I don't know, so you might say that you have 10 features, you need 10 layers, not necessarily, but again, this might be something, maybe not because of the feature, but maybe because one feature could contain specific things. Maybe you need more layers actually, right? Or maybe, right? You only have a few things about specific to your data, right? You don't need these layers, right? So here's something image recognition, right? So network is training network for image recognition. Your layers, some layers can recognize basic shapes, triangles, squares, right? Of course, nobody's going to tell you like that. There's not going to be somebody, model will tell you, okay, I know shapes now, I know kung fu, right? So no, there's also going to be later maybe recognize some textures, maybe your hands or faces or models, whatever, right? So they will be very obscure, right? So you won't be able to understand these people. Then together, right? Hopefully, right? You can get some numeric representation of exactly what you want, right? So yeah. So basically, what the book says is still true, right? It's basically experience intuition. So, right, it's like how chefs experiment with recipes, right? So idea is you need to iterate quickly. You need to change. Okay, this works. Okay, this is good results, right? And that's all. That seems all nice. Of course, again, mathematicians are really upset because this really, you can't really, it's almost impossible to prove things. But I'm going to stop here. So here's an example. Convolutional networks. We'll talk about convolutional networks next, right? So one of the challenges, you have an image, right? You want to preserve the relation of pixels, right? If you give it a big, if you convert your pixels to one big array, right? You're going to lose this two-dimensionality of the image, of course, right? And your network, right? If you're building it, you're training it, it might not remember, it might not learn well enough. So one of the things used for this, one of the improvements is something called CNNs, right? Convolutional neural networks, right? So there is it takes advantage of spatial adjacency, meaning what pixels are next to each other, right? So it adds these local connections, initial layers, right? So and then so it respects this, pixels being next to each other, basically, right? So very very cool idea and works very well, right? Um, yeah, so of course you manage shape, right? So again, so of course there's a lot of batch processing, of course, right? So uh, if you want to go deeper, right, then the next step is residual networks, right? You want to be very deep, multiple layer network, right? Because one of the problems is that something called the vanishing gradient problem, that your feature, your data basically could. So something that's important is each new iteration and each new epoch basically might just fade away, right? So, you can add this extra step that you preserve the previous representation, basically, right? So you learn these residuals, these changes, right? Residual stands for basically, you say errors, statistics residuals are errors, right? Residual, right? Changes or deltas, you say, right? So they books as perturbations, right? So changes basically, right? So you add the output layer back to the input basically through short connections. So so it seems like it's like learning from your previous level basically, right? Yeah. So very interesting problem and used a lot. So again, so training means you adjust the parameters to minimize the loss function in the training step, right? So it seems like the actual learning algorithm is mostly gradient descent. Right? That's basically the core part, right? So yeah. So again, the changes, the training sets. Maybe you can do a gradually decreasing learning rate. Maybe you adjust the shape, the movement, maybe slower, right? Maybe possible, right? Again, so again, and of course, at some point, your model is going to be learned, it's going to be overfitted to exact data, right? And it's going to start becoming less useful to other data at some moment. It's going to be perfectly learned, even 10, 100,000 or 100 million points, data points. It will be ready for that particular data, but to some other outside data, right? So that's the thing. Right? Overtraining actually could also happen, right? So, right. So value propagation, right? So because the information coming in, right, of course, goes forward and backward basically, right? Thin layers. Pretty simple idea here. Right. So propagation, right? So you propagate that information backward from the output layer to the input layer, basically, right? So how well do you do, right? So this is a very extremely common, of course, to be included, of course, in most machine learning libraries, right? So batch normalization, enhance the rate, this one, the batch rate normalized outputs, right? Adjust the scale to related accusations. Okay, so basically, if you remember, we don't want the model to learn perfectly on the training data. Our main goal is it wants to be generalized, right? It's not very useful if it knows if you can answer perfectly on the data as already see. We see this with ChatGPT in most of the problems, right? It's not very interesting if your model can make predictions on something that's seen. You want it the models become very powerful and it can generalize something on novel, new tasks, new queries, right, new predictions, right. So that's the main primary objective in machine learning, right. So of course, to enhance this generalization, right, so appropriate network architecture, right. So how big your network, how deep your neural network will be, right, types of layers, connections, right. So again, there's tendency to maybe okay, have new hardware, right? Build this very deep network. Maybe you need many layers. Maybe it's not just few layers. Maybe one or two layers in a shallow network will be fine, right? So what's interesting is right is something called drop off. Basically turning off your brain at times, basically like in the real, right? Some part of your brain, right? So sometimes stopping some parts of learning, stop it, right? This can force the network to learn some features which are very more robust features, which are not relying on specific paths, right? So this might improve on generalization, right? Also, you don't want a single input feature dominating, right? So that means, of course, regularization, normalization, right? All features are equally important, right? So very common for this. There's penalty for you want to penalize like some specific feature, basically, right? So how do you choose it, right? So empirical evidence, I tell you, start with shallow ones, right? But empirical experiments, right? So, given similar number of parameters, offer better generalization, right? So house numbers, right? So 11-layer network offers 0 network contested rate, contested error, right? Let me see if I can show you some examples, right? So deep learning errors. So the problem, of course, is that we still getting some, weird predictions, right? Hallucinations, right? Because again, you don't know, you can't explain particular hallucination, right? This particular prediction. Why this network given these particular weights, gives you this prediction. It's impossible, basically, right? So, all we can do is we can try to minimize errors, keep this ongoing process, right? The problem is, of course, that really large data sets, of course, require, of course, a large computational power. So, of course, you do smaller batch sets, right? With simpler network architecture, right? With simpler evaluation functions. I wanted to also show you RNNs, long short memory, right? Use this no CR quite a lot actually, right? So basic idea is that we have this sort of, again, I'm saying quotes, memory cell, right? So, which carries information between many epochs, many time steps, basically, right? So, it regulates all the information out. This works really well for OCR, speech recognition, handwriting, whisper, and all those things, right? So this works really well, right? Again, couple more terminology things, right? Supervised learning, right? So we sort of like have a bunch of data, right? And we get also some models, but of course we don't have anything to compare this. But it's transfer learning, right? Very important thing now. We have an existing model, expensive model. Some machine learning engineers spend a lot of money on it, right? DeepSeek, right? Or I don't know, OpenAI not giving us our models, right? Or Llama, right? Yeah. And then of course you want to adjust to your task, right? That means, of course, transfer learning, right? You want to enhance it, right? So here, as I mentioned, semi-supervised, right? Maybe you have a small set of labels, some larger set of full labels, right? So that's also dominant, right? So supervised learning, right? We of course in supervised learning, we want to learn the mapping, right? Because we want to predict something, right? So level data, right? We want to learn some new data representations. That's a possibility. So, PCA. PCA is basically, we have a lot of dimensions. We have data, rows of data, say, with vectors of hundreds or 100 dimensions, basically, right? Not very useful. We want to usually generate, 2 dimensions for display purpose at least, right? Because we can visualize 2 or 3 dimensions. We can't visualize 100 dimensions. Yeah. So there's ways of using probabilistic for open analysis. There's also, of course, random PCA also, of course, right? Right. Also, something called auto-encoders. You have some data, and you want to encode them into compressed representation, right? So, all right. So that's also very, very promising area. And of course, GNN, very fun thing. When this book was written, 2019. GNNs were very cool. I mean, this is like the new hottest time, sort of before GPT. You might have played around with it, seen maybe some demos of this. So idea is, I think I had one person in bachelor's last year who did bachelor's on this. So you have somebody who generates, right? You have a judge. Basically, you have like a producer or a artist or student, and then you have this judge or discriminator, right? Model, right? You said, okay, this is a good example, this is a bad example, so right, classifier, right? And so the generator hopefully comes up with some good examples. Let me show you some ideas from generative adversarial for our examples. The air examples are kind of cool, right? You can still do it, right? So basically, you give it the generation, right? You give it you need to judge as generator. Slowly realize the student slowly realize this network realize what makes for a particular art. Teachers like you're probably like this too. You slowly learn, but each teacher likes what kind of assignments and what kind of answers they like, basically, right? You're like that too, right? Everybody's like that, right? So that's it's still used. It's just not the only thing, of course, right? So translation, of course, transfer learning, applications, lots of applications. Right? I want to see if I have an example for you. Lots of stuff here, lots of information. So, yeah. Reinforcement learning. I'm going to do this next. Oh, yeah, we're going to do that next on Thursday. We'll do reinforcement learning, right? So, So, of course, what's the reinforcement learning? We have a reward, right? Yeah. We have a reward for agent, candy, carrot, right? To maximize. So this is something you can learn using this reward function, right? You can learn the value function basically, right? So, of course, for games, right? Reward is, of course, the game ending state, right? You give that reward function basically, right? So it has some really big successes. We'll talk more about this next on Thursday. But I thought I had a little example how you can do encoding. The books. I'll show you an example of. I teach called the simple neural network for digital recognition. Let me show this example. We have like 10 minutes, maybe we can do it. Let's see. Example. There you go. Example of a administrative recognition using simple right. NIST emission. Let's see. TensorFlow, I believe. Yeah, I think I should show you. Actually, I think we will link to this notebook, right? It might be still up. So GitHub, Google, TensorFlow, NIST, NIST, I think NIST. NIST, yeah?
Yes.
NIST,
Yes.
NIST,
With the N, I think, in the middle.
NIST,
Like NIST, I think.
NIST.
Yeah, if I recall. No.
I showed you last week, I mentioned this too, right? I think M and NIST. I think.
M and East. I think.
Yeah, NIST.
Yes,
NIST,
yes.
Okay.
Smart.
Hold on, notebook. Let's see. It is an official Google materials, right? Like it was like 6 years ago, right? Let's see. Yeah, I think this one is it. I think this one looks like it. Yeah, this is actual official one, I believe. Right. Let me give you a link to this, right? This comes from Google, GitHub. I believe MIT from MIT. Yeah, very simple example, right? You'll need to download the progress bar, right? You can do this actually right now. Let me give you a link to this, right? It's a really simple example. I'm gonna do it myself, I don't know. Yeah. You see what the other one is. This one here is experiments. That sounds like experimental. Yeah, this one is, I think, is the older one. But this is Craig Collab. I don't know who that guy is. Right? Yeah. This is old. So this one's pretty old, because I'll be shocked if it still works right there, right? Because TensorFlow is famous for changing API, basically, right? So if you start playing around, and you look at the school tutorial, you want to run it, and then like half the API is not working anymore, right? So don't be surprised. That's why, of course, people move to Keras, because, and also, of course, to PyTorch, which is from Facebook, right? Simpler. Now, but let's see, this will be interesting to see. Example, this still works, right? Or not? Right, let's show you an idea. This still works. Yeah, we all know two from this one from a while ago. Right, so if this still works, let's see is this guy still on? Let me see. I'm going to show all my emails. I don't know.
I think because it's saved in the Chrome password manager.
Yeah.
And the password manager can be accessed by incognito, so.
Cool, very cool, very cool. Like, this being somebody, the question when does that become accessible, basically? When they log into what account? Because.
Well, if you have a two-factor authentication set up everywhere, then the cookies should be cleared everywhere.
Yes, that's the problem. I have like 10 different Gmail accounts. Some of them don't have two-factor, some do. And the question is, which moment does it start leaking? That's scary stuff, okay? All right, so let's say this experiment works. So we connect. So this is the basic idea I showed you last week, right? Okay, so TensorFlow 2, let's see. Yeah, okay, it's not authorized, okay. Let's see if this works. We should have 311, right? 311. Okay, so yeah, so this is newer version. That's good. Actually, it should work. Let's see that all. Yeah, okay, 3.8. Here, that's on 3.11, 3.11, and 2.18. Here's 3. Okay, that's pretty decent. I don't know if we need this one anymore. Okay, remove any logs. It's going to be all the very dangerous command, right? Mm-hmm. Yeah. If you had a little star here, you remove all your drive. Clean. Okay, so basically, Terra's TensorFlow includes for free, basically, right? So 60,000 training, 60,000 images, 28 by 38 pixels. So that's, I told you, 576? No, more, 784, I believe, right? Yeah, 784, 784, right? That's it. Thanks. Right? So we can check. Oh, yeah, downloads, okay. Oh, we download it. You bring the shape right now, just want to check the shape. So let's see, 28 and 28. Right? Yeah, 784, okay. Now, so imagine the shape, right, in the channels. Again, you only have one channel because, of course, black and white, right? So, all right. Yeah, again. So data is basically in data frame, data frame, right? Suppose it's just that one bit. Basically, if you train it, 28 by 28, basically, right? So you can see roughly here is this what is the number? You see this? It's
5.
5. Yeah, looks like 5, right? Yeah. No, looks like right. And also, what's the answer? Yeah, you see. Oh, you see this? Yeah, 5. Yeah. Okay. So you can see the training examples. All right. Again, you can see there's sort of a grayscale, right? So it's not like 0, 1. There's also, there's shades of gray, right? 255 shades of gray. All right, so we will shape the data. So, to the 8, right? We will shape it. So, again, this is so potentially you have multiple color channels. We won't have it in this example, right? But there's a lot of stuff when you do machine learning or just basically matrix, basically just shaping data, adding some extra levels, basically, just sort of like W wrappers, basically, right? So okay, now it looks okay. Maybe basically a tensor, right? So we're going to normalize, and this is just linear normalization, 235, right? Because it's up to 235 for learning, we want from 0 to 1, right? Okay, so that's basic stuff in reality. So now we're going to build a model. So this is where the actual stuff happens. Sequential, right? We're going to have that. Let's see what's this one going to have. Sequential. You can use a correlational layer, right? A max pooling layer, correlation 2, 1, 1, 2, 3, 4, and flatten layer, right? Of course, know this last thing, right? We have this requires knowing what you're trying to predict, right? Last step is important. You want the 10, right? You want the output to be, 10, right? Because otherwise, you have 500, right? It's not going to be very useful, right? Because, so, again, let's see if this works. This still works, okay? It should print you a summary. Okay, so, layers, commercial, right? Commercial 10. Yeah, so now, the shape is 10, right? So, 10 is the most important part. So why does it say, okay, where's the input part, right? So, okay. You know, you print it apparently. It works. Yeah. You can print or layout. So now, of course, you compile it. Again, depending on your model, right? Now, of course, the actual work happens here, right? You're going to do 10 epochs, so 10 times. What's the loss function? The loss function, I didn't see this, the loss function, loss here. As far as the vertical cross entropy, right? So you say, okay. And metrics, of course, accuracy. How well it does, right? Let's take a look. It should work pretty well. Again, because this is, again, these digits are pretty easy, right? So we can do this in a couple of minutes.
You have to tell a joke.
Yes.
You have to tell a joke since we have.
Oh yeah, we have 10 epochs to do, right? The joke for machine learning. Oh my god, so you didn't tell a good joke. Anyone? No? No? Not clean jokes, No, no blonde. It's completely blonde here, right? So, well, you are kind of blonde, right? Yeah, a little.
Words won't take it personally.
All right, then fine. Okay, I'm making a mistake.
Oh, actually starting?
Yeah,
No,
Yeah, just okay.
we can have like,
Take that.
so about a minute or 2 minutes.
Nu, Karš, 3 blondītes, sorry, bet sievietes. Izdomā, ka brauc ceļojumā pa tūkstnes Sahāru ar mašīnu ceļojums, vai ne? Viņas noīrē mašīnu, brauc visu foršu, pēkšņi mašīna noplīs, viņas ir tūkstneša vidū vienas, tas, ok, ko iesāk zona, nav kam uzzvanīt, iesim ar kājām. Nu labi, tur mantas smagas, jādomā, ko ņemt līdzi, vai ne? Nē, bija viena melnataina, viena brunete un viena blondīna.
Okay.
Jā.
Change things, okay.
Jā. Sorry. Tur ilgi domā, ok, krāmē, sāk iet, brunete prasa melnatainajai. Nu, ko tu paņēmi līdzi? Es paņēmu ūdeni, jo tā kā karsts un tūkstnesis, kā slāvst. Mēs dehidrēsimies slikti, vai ne? Jā, ļoti labi izvēle, gudri. Ko tu, brunetei? Es tā kā paņēmu saules krēmu, jo kā saule, tūkstnes, bet apteksim, ādas vēzes, visu slikti. Jā, arī ļoti gudri, jā. Prasa blondīnei. Ko tu? Es paņēmu mašīnas logu, jo es tā kā atvēršu logu un atvēsināšos no vēja.
Okay, all right. Okay. By the way, think of this joke, but there is actually a task in psychology, as journals will tell you, this where they do this task, they give it to people. All right. I don't know, but so there was the conference where basically you have these volunteers like you probably get paid for this, right? And they give you this task. One of their tasks is exactly like this joke. They give you a list of 15 items. And you have to get the consensus, what to prioritize, what do you take first? Like water, umbrella, or but it's hilarious. There's the option of parachute, like because you already have a plane crash, basically not cheap, but plane crash. So you could take a parachute with you. And I was looking at this data. This is some people think that it's a good idea to take with you on your trip across the desert, right? But I guess there's some justification because I guess you need some shelter. I guess you can use it as a shelter, I suppose. So water, of course, yes.
I think the justification was that you can lay the parachute down and during the night you can gather some water.
That might be, yes.
Also,
Yes, because you've seen that even in desert, completely dry area, you can still get some water. You have this condensation, like this kind of thing. There's this life hack, right? Assuming you ever are in Sahara, right? So maybe the blonde was actually smart. Maybe she could use that, whatever it is, like I don't know, the window, right?
light the fire.
Yeah. Okay, we're almost finished. Again, of course, obviously, let's check what's happening by the way. To see accuracy, right? So we're getting better, right? 99.38. So what does this mean? This means that almost 99.377% of answers in a training match, right? Again, that does not mean anything before we start testing, right? Because maybe just fitting exactly to the test type. But assuming we had a random, the 60,000 were randomly selected from those, and 10,000 for testing also randomly, right? That should give us a pretty good idea, right? This can generalize pretty well, right? Let's see, we're almost finished. We are finished. All right. So this is the news, this is such a work. Right. So we'll plot the epoch. We already saved the epochs. Yeah, we are saving history. Right. Loss. So you can see this here, right? Ready? Okay. Yeah. So again, expect that the loss get better. Oh no, it's not finished. No, it's not done. Sorry. So these are batches that will be this number here. It batches into these small sections of data, and you got that. Sorry, you got this correct. Yeah. Oh, because here you see good. Oh, it's still playing. Okay, yeah. So you can see, initially, right, the first echo, right, one echo is not going to be good enough, right? But this, of course, doesn't use matches. So, and same was
What
backwards.
was the loss parameter on this ruling?
Is
On
it-
the y-axis loss.
I mean, loss value, right? Loss value. So, what is the loss function here? Let me see here. I missed which one it was. So accuracy is percentage. So they are of course very close. So they don't add up to one, right? So loss function in this case. What is the loss function here? Let me see if I can find it. Loss function. Training loss, training accuracy, right? So you see, it's not quite, they're very closely related in this case, right? But we actually not almost here, yeah. So, yeah. Evaluate, okay, let's take check, let's check. The loops, so loss is very small. 9 loss, so the loss function in this case. So it's kind of like reverse accuracy, right? It's not the same thing. Because you split a different function. Let's see which one to use. Let's keep this.
Yeah.
There's no option here. Somewhere there's no option is. And I missed this here. Okay, the measurement here. So, functions.
Yeah, but still not very.
So it's kind of like reverse accuracy, but here, sparse categorical cross entropy. Okay, that's one it is here. All right. Which one it is? Which one is this one? Okay.
But what does it actually mean? Because
Okay.
categorical cross.
Yes.
entropy.
So, the term sparse. Okay, here's the example. Okay. Let's look at the example to make sure. All right. So, y through 1, 2. Predictions 0, 9. Okay, loss this is like a, can say 1, 2, there's 2 dimensional flu vector, so predictions on this vector is giving us, right? And so it gives us, you get the solution, this one is sparse. Why is it sparse, right? In chaos, was chaos? Or Python, that's a law. Yeah. Okay. Two or more label classes, right, is integers, right? You can use, okay, so it's not one code, because it's sort of, we have this one, we're not using one hot here, right? So we're kind of skipping that part, right? So, probably what's the formula? I mean, it just gives you the example, it doesn't give you the formula, right? So y true and y predictions, right? Probably calculate. It's a formula basically for this. Again, if there's any loss, smaller is better, right? Yeah, not much everybody understood, right? So, but exactly, is it helpful? Not too helpful, right? Because it doesn't give you the formula, it just tells you, right? Right, from logics, arguments, yeah. So, because you want to come to zero formula basically. You basically want to say how much information you're losing basically, right? So, but on this, I can't come up with the result here, right? So,
it says that the y predict is the probability distribution.
Yes, that seems like that's what you see here.
saw it somewhere.
Yeah.
Yeah, the second paragraph says.
Yeah. Okay. Yeah. Yeah. Okay. No. Yeah. Absolutely. You see? Oh, you can see the source. That's good news. Let's see. What will help us? Okay. Alpha, gamma.
It's lower down, I think. Yeah.
Oh, there. You can see the exam. So that's of course the offspring. You can see exactly what it does, actually, right? Binary labels -1, right? Go to the right.
No, but that's I think already the next.
Yeah.
Wait.
Yeah. So I can't give you a formula offhand, basically, right? Basically, as you see, it basically shows for again how close predictions are, right? Basically, right? So that's it. So my answer is like, I can tell you what it is, but I can't give you exactly this particular loss function, right? Yeah, I usually, of course, check. Easier for me, of course, I know the accuracy, right? That's I usually check, right? So they want the alpha loss. So let me finish this. See, this actually they're finished. So, okay, we can say the model now, right? Was typical, right? Keras HDF, because we can download afterwards here on this computer. But again, I told you it's depreciated, the Keras 3, right? Okay, so HDF file, we can load afterwards. How it works? Yeah, okay. I thought I see metrics now. Okay. Yeah, the method. So we made the predictions. So we created all of them, right? So what we'll do is in this model, right, it will give us the probabilities of what it should be, right? So this should be 5, right? I believe, right? Where is it? There's a big one. This one, right? 7. So where's the 7, right? No, 5, right? Where's the big number? You see? Which one is the big one? Minus. Where's this one? 7. Okay, yeah. So it's 90.99999% sure it's 7. Well, not 7, 8, right? 8. So 0, 1, 2, 3, 4, 5, 6, I guess 7, right? Let me see, let me check this. What was the first one? Right? So those are the answers. So it gives you probability. So you can see here, it's extremely sure for these, right? This is a very easy example, right? Right. So, yeah, so 0, right? 7, okay, so it's, yeah, it's not good. So it is indeed 7, right? Yeah, 7. Yeah. I want to see, okay, yeah. So this is like, I'm not doing, so it's kind of nice to see where it makes mistakes. It's going to be nice to see. Right. So this one is, I think it's 4, it's actually 9, or is it 4? I can't tell myself.
We've read so it's.
So it should be 4, but it's actually 9? Or is it?
No, it should be 9 because it's.
Yeah.
Because the image is 9. Huh?
Yeah. So it thinks it's 4, but it's actually 9. So, but like, I could see it being 4. Right?
Because of the gap in the top.
Yeah. That's it. That's the only thing that I know is 99.9 accurate. So it's pretty works pretty well, right? Right. And then according to a conclusion matrix, right? So see what number 4 values gone, right? You can see the debugging, right? Things like that, right? With that video. We do a format for logs. Okay, so yeah. But basically, the magic is that we can remember that, of course, loss function is important, accuracy is good enough, right? Loss function is not critical, you know. But this part here, of course, this part here is our model, right? Normalization is important. But this part here, you play around. You take off a couple layers, right? A couple layers, see what happens. Of course, here it works so well in this example, you know. For example, if you have 20 different answers, right? Then of course it's very simple. You add 20 here, right? And that's it. You have your answer for 20, of course, right? Of course, you have also your answers 20, right? So, or only two, red, binary classifier, right? Red, yes, no, other, right? So pretty simple. You do the principle, right? And here, of course, the regular data, 60,000, that's not much. And also pretty tiny, 784 features, right? Not too big, right? So simple neural network, but you can see what's involved. You do the demonstration. I can save them, yes. I can save it. Where do I save it? But that's not my GitHub. Right, so it's gonna
Save it for someone else.
I'll save it. Oh, it's open drive. Yeah, I'll save it in drive. Yeah. That's my colleague, my colleague. Okay. So Thursday we will check on reinforcement learning. We'll see what to do with our normal.
Okay.
We also want to show you some information on these neural networks. So we'll see, maybe we'll do a little run, a sample run, I'll show you some results, hopefully, maybe, of your bots.
I think you should test our bots on your own models prior to the lesson and only during the lesson the competition.
Yes, okay, pure competition. Okay. All right, so thank you, everyone. I'll see you guys on Thursday. Yeah.
Ik kan dus.
Okay, normal. Okay.
Uzlabot, jo kaut kāds potenciāls tur bija, bet kaut kas greizi.
Jā, bet kaut kādā veidā, ka nebija trenējies finansīgās vecā.
Jā, varētu būt.
Jā. Tā arī tā, ja tu arī nav gribēji kaut ko.
Jā, tas ir saprats, ka nē, jo. Konverīt.
Bet godīgi, es nebiju domājis, tas, protams, ļoti jauki, es mēģināju domu, kādam citam projektam vēl tagad kādam būs neural networks var izmantot. Tā kā tam būs vēl iespēja.
Jums nav kāds sūdzējis, ka tas ne Mārtiņu brīdum, tad servers kā tāds neatpazīst uzvarēts.
Viņam bija jādod ziņojums, ka ir pabeigts kaut kas. Jā, tur bija jābūt ziņojumam. Kā jā, bet vai viņš to nevar precīzajā specifikācijā. Viens man nav sūdzējis, tur bija paziņas mainījās. Jā? Tur mainījās tā, tikai vai mainījās pareizi, tas ir jautājums. Jā?
Nē, jo vienkārši, to jūsu random pārsvarā, viņš vienkārši uzvarētu ar prostā līnijā. Mēs to auto diskrintēju ārā, lai šis ir pārkautība, ka ir 5. Un viņš ir, un man tā mini-max funkcija, ka šeit tāda.
Jā.
Viņš, ka tā funkcija kā tāda saprot, ka nav vairs sakarīgi mūlu, jo ir 5 rindiņā, viņš